At the Atomic Energy Authority's research establishment at Winfrith Heath, the various processes will produce active and non-active effluents. It was planned that the slightly radioactive effluent should be discharged 2 miles out to sea. This involved the laying of a pipeline 6 miles overland from the site to the coast, and then out 2 nautical miles. The contours of the land through which the pipeline was to be laid varied considerably. At the 6 lowest points had to be installed. While at the higher points, air valves were fitted. At the highest point in the line, 275 feet above sea level, were brake pressure tanks. At Winfrith, the active effluents will be pumped from the various buildings to delay tanks through pipes laid in ducts coated with chlorinated rubber paint to facilitate decontamination in case of active leakage. Effluent from the delay tanks will be sampled before being pumped to dispersal tanks next to the master pump house. Non-active effluents will be pumped direct to the dispersal tanks. From the master pump house, the overland pipeline was designed as a pipe resting within a pipe, the active effluent being discharged through the inner pipe and the non-active effluent through the surrounding space. The idea of a pipe within a pipe is a double precaution against any possibility of the leakage of radioactivity into the underlying strata of water-bearing chalk. The route of the pipeline was planned primarily to give ease of access to the washout and air valve pits at all times for maintenance. For instance, should washing out the pipes become necessary and there is any possibility of the liquid being active, it will be pumped direct into mobile tankers. Any spillage from the air valves or washouts will be contained in the pits and removed in the same manner. The route was also planned to avoid undue disturbance to agriculture and the surrounding farmland. The pipeline should be considered in 2 stages: overland to the coast at Arish Mell, then the next stage of 2 miles out to sea. It was no ordinary pipe-laying job, and a number of tricky engineering problems were involved. In many ways, the project was unique. The overland line consists generally of a 6-inch pipe inside a 12-inch pipe. The pipes are mild steel tube, 3/8 of an inch thick, coated with bitumen inside and out. 3 40-foot lengths of inner tube were first butt welded together, and the welds radiographed by gamma rays. When found satisfactory, the scale was removed from the inner weld by a rotating flailing head, and the interior coating of bitumen made good at the weld. The same procedure of assembly was followed with the outer pipes. 3 lengths were welded together, and the external protection of bitumen asbestos sheathing, reinforced with woven glass fiber, was made good at the welded joint. This method of pipeline construction was carried out over the 6 miles of land line. To prevent damage to the internal coating of the outer pipe, a carriage was fitted to take the weight of the inner pipe as it was inserted. The length of pipe within a pipe was then lowered into the trench and offered up to the leading end of the pipeline already laid. The inner pipe was lined up, butt welded, the weld descaled and radiographed. When the radiograph showed that there were no defects in the weld, the same drill took place with the outer pipe. As a check on the standard of welding, about 5% of the welds on the outer pipe were also radiographed. The external shielding was tested and any defects repaired before backfilling. Wherever possible, as soon as the section was completed, the trench was filled in, the land restored. Some points, however, had to be left open for the construction of air valves and washout pits. The depth of trench was such as to provide a 3-foot minimum cover over the pipes. Road crossings were necessary at 6 points, but only one of them was under a main road. Here the pipes ran through a concrete culvert protected by a reinforced concrete slab. The culvert has an access and inspection chamber at the end and is long enough to allow for the proposed widening of the road at a later date. Under minor roads and farm tracks, the pipelines are also protected by reinforced slabs of sufficient length to allow for future road widening. At the highest point in the line are the brake pressure tanks. Up to this point, the effluent is under pressure from the main pump house. From here onwards, the flow is by gravity. Each of the brake pressure tanks consists of a steel tank into which the inner pipe is welded and surrounded by the concrete tank of the outer pipe. Thus, the principle of a pipe within a pipe is maintained. About 1.5 miles from the coast, the pipeline runs through the grounds of Lulworth Castle, built in 1588, the year of the Armada. After leaving the castle grounds, the pipeline makes its final under-road crossing. Beyond this, excavations were being made for the last air valve pit of the line. As with the other air valves and washouts along the line, the branches were welded into the inner and outer pipes. From here, the line ran through the War Department's gunnery range, and the depth of trench was increased to provide a minimum of 8 feet of cover as protection against ricochets and the passage of tracked vehicles. On the flatter sections of the gravity side, larger diameter tubes had to be used, but from this point, the rest of the overland run sloped steeply downhill, so the diameters were reduced back to 6 and 12 inches respectively. For 200 yards through the ranges, the pipes were encased in 2 feet of concrete with 10 feet of earth cover, as this section was in a direct line of fire. Alongside are the cable ducts for the supply of electricity to the shore valve house and for the cathodic protection system of the sea line and the shore end of the land line. And so, the 6-mile overland pipeline continued towards the shore at Arish Mell. Just above the high water mark, the shore valve house was being constructed. In this reinforced concrete chamber, the twin pipe-within-a-pipe landline was to be divided into 4 separate 6-inch pipes. 2 of these, carrying the non-active effluent, were to end 50 feet beyond low water mark. The other 2, carrying the active effluent, were to be connected to the sea pipeline. This was to be a twin line, 2 miles in length, and provision had to be made for an assembly and launching area. This meant the clearing and levelling of several acres of land running back from the shore. For the sea line, lengths of pipe 6 inches in diameter and ½ an inch thick were assembled on the storage racks, and then welded into 1,200-foot strings. Every weld was radiographed, descaled and bitumen coated, as in the case of the land line. The completed strings of pipe were checked for internal obstructions and air pressure tested to 100 pounds per square inch. The external bitumen asbestos coating was of course continued across the joints. Before launching, the pipes were covered with a casing of concrete 1½ inches thick as a protection during and after pulling and as an anchor for the line. The pipe was surrounded by wire reinforcement held away from the tube by small spacing blocks. Metal shuttering was then placed around the tube and the concrete poured. Vibrators applied to the shuttering ensured that the concrete was well compacted. The thickness of concrete round the 600 foot of pipeline at the shore end was increased to 3 inches as an added protection and anchorage against wave action where the water is shallowest. The laying of the sea pipeline from Arish Mell to a point 2 miles out to sea involved a great deal of underwater work. A survey of the seabed had shown that there were 7 main reefs running across the proposed line of the pipe. The inshore reef was a chalk barrier, 225 feet in extent. The next one, Kimmeridge clay, 400 feet. Then came 2 of Portland stone, 350 feet. The 3 outer reefs were of black shale, 1,125 feet together. In addition, the survey also determined the distance from the shore of each reef and the depth of water above it. The chalk reef was 600 feet from the shore in 23 feet of water. The next reef was 2,125 feet out and 50 feet below the surface. The 2 Portland reefs were respectively 3,100 and 3,850 feet offshore in 54 and 60 feet of water. The 5th was 4,500 feet from the shore, 69 feet below the surface. The 6th was 6,175 feet out at a depth of 74 feet. And the last reef was 7,350 feet from the shore in 82 feet of water. Through these reefs, a channel had to be blasted. Over 3,500 cubic yards of rock had to be removed to create a smooth channel so that the pipeline, when laid, would not flex to a sharper radius than 1,500 feet. When the whole of the line had been laid, a prefabricated diffuser assembly was to be lowered and fitted to the end. This then was the problem. The project itself entailed 6 months of underwater work, all its attendant hazards. This stage of the project was unique. It was to be a line and level job. One of the authority's site engineers, specially trained as a diver, made a detailed survey of the reefs through which the channel would run. Sea lines have been pulled out before, but this one is unique, not only because it is believed to be the longest sea outfall in the country, but because of the number of rock reefs through which it had to be pulled. These reefs necessitated the preparation of a trench to an accuracy of profile and relative smoothness not previously attempted on such a scale underwater, and called for rigorous and detailed inspections at all stages of the work, in the same manner as for the foundations of a building on land. Checking the general trench profile and detecting local projections and hollows was facilitated by the use of a specially developed pressure gauge capable of measuring depths to an accuracy of plus or minus 3 inches. A variety of vessels was employed by the contractors on the job from which the divers operated. Their work, of course, depended very largely on weather conditions. The drill for all vessels was the same. Each day they took up their allotted position in line, taking their bearing from the shore marks. A special submarine explosive was used for the blasting charges, kept in a store on land. The authority had the services of an army duck. This was most useful, not only to transport the charges for blasting, but to maintain a shuttle service between the ships and shore for stores and personnel. Each ship carried at least 2 standard divers. As soon as the vessels were in their allotted positions, the divers went down to start the day's work. The charges, already primed, were then dropped down a shot line to the diver waiting below. Released from the shot line, these were carried by the diver and placed on top of the reef to be blown. While the charges were being laid, a skin diver was getting ready to take down the fuse. Skin divers were employed to service the standard divers. Their greater mobility saved much time and helped to speed up operations. When the charges had been laid, the fuse was taken down to the standard diver for connecting up. The area was then cleared of divers and the charges detonated. Around the area of each charge, an air cushion was created to reduce the effect of the blast on marine life in the neighborhood. After each blow or series of blows, the authorities' engineer inspected and checked the results. It was known that the blasting would cause a certain amount of cratering, but in the main, the rock was so well fragmented that it was proposed to fill in these craters by sledging. Sometimes, however, additional blasting was needed to remove high spots or boulders. Small charges of explosive were enough for this, but the underwater drill was the same. These small charges were sent down on a line from the ship to the diver for placing in position. When all the major blasting was finished, the whole channel was scraped clear by a sledge operated from the surface. This sledging cleared excess rock, filled in the craters, and generally smoothed out the channel. A final inspection and check of the whole channel was made before the pipeline was pulled out. As the preparation of the channel neared completion, work started on getting the sea pipeline ready for pulling out. Side boom tractors lifted the first length of pipe from the storage racks to rail bogies running parallel with the racks. Travelling bogies were used to avoid damage to the concrete covering of the pipes. Each pull was to be a string of twin pipes 1,200 feet long, held apart at 22-inch centers by shaped wooden blocks and strapped. Buoyancy tanks were fitted at 60-foot intervals to reduce friction between the pipe and the seabed, so that the line would ride lightly during the pulling out operations. At the pulling end of the line, flanged joints at the ends of the pipes were bolted to the pulling head assembly. On this was fixed the leading buoyancy tank and the pulley for the hauling cable. With a crane lifting the forward end, the pipeline string was moved down to locate it on the rubber-tired guiding bogies leading to the sea. The string was steadied by side boom tractors as the end was lifted by the crane. Out at sea was the colbar, a specially adapted barge, fitted with the main hauling winch for pulling out the pipeline. 4 specially designed anchors, individually controlled, enabled her to maintain her exact position in the direct line of pull, irrespective of movement of the tides and currents. The hauling cable from the colbar was now threaded through the pulley on the lead assembly and took the pull. Between high and low water marks, a deep trench had been dug and protected by steel piling for the launching operations. With the pipe string in position, frogmen made the final checks. The crane was unhooked from the float, and the first pull started forward into the water. Each buoyancy tank carried a release gear and marker buoy. As colbar hauled, the movement of the pipe was controlled by a hold-back winch at the far end of the storage racks. The cable from this winch ran to clamping gear fixed to the end of the pipe. A strain gauge on the winch gave readings of the hold-back tension, which were relayed by radio to the control tower. At the same time, on colbar, a similar gauge indicated the pulling strain, which was also radioed back to the shore, so that the pull and hold-back tensions could be balanced by instructions from the control tower. As the pipe moved on to the rubber-tired bogies, so its weight was removed from the rail bogies, which ran clear, ready for use on the next pull. Underwater inspection, as the pipeline was pulled out along the channel, showed that all was well. The size of the first tank had been designed to give the head of the line a slight lift to hold the leading lengths clear of the seabed and thus facilitate the pull. In its final position, 2 miles out, the towing head will be removed and the diffusers bolted to the flanged ends. As the end of the pull neared the shore, provision had to be made to secure the end of the pipeline. 2 cables held by dead men were fixed to clamps on the pipe so that the holdback cable could be released for fixing to the end of the next pipe string. A strain gauge fitted to the dead men registered the tension in the restraining cables. The next 1,200-foot string of twin pipe was assembled and strapped. And then brought up to the end of the first pull, till one pipe butted on the other. These were clamped together and butt welded. Rather than try and locate both pipes exactly, it was decided to cut back the second pipe to make a standard 11-inch gap, which would be filled by a prepared length of pipe with a wall thickness of 11/16. As it was impracticable to descale the closing weld or to coat it internally with bitumen, the thicker walled pipe offset the lack of anti-corrosion protection normally provided by descaling and bitumen coating. The welds between each 1,200-foot string were radiographed. The radiographs were immediately developed and examined on site. When the weld had been approved, it was bitumen coated and wrapped with fiberglass. And a further coating of bitumen applied. Throughout the length of each string, a high voltage detector was used to check the continuity of the bitumen coating for the presence of pinholes. The joints were made good with quick-setting concrete. Covered with sacking, and a further coating of bitumen applied to protect the exposed surface of the freshly poured concrete. While all this was going on, the next set of pipes was being moved into position. Even with their coating of concrete, they flexed without damage. Ten separate pulls were necessary to take the pipeline out to the full distance. Each pull took about an hour and a quarter, but the operations between pulls of assembling the strings, welding and concreting the closing joints took an average of 6 to 8 hours apiece. One point on which early checks were advisable was to see that the concrete casing was doing its job of protecting the bitumen-sheathed pipes during the pulls. Day and night, the work went on. Even after making all allowances for the known tide and weather conditions for the time of year, there was always the possibility of a sudden storm blowing up. In fact, on the second night, pulling continued during a force 7 gale. In spite of this, the whole 2-mile pipeline was successfully pulled out in 5 days, 2 days less than had been expected. To speed up inspection and avoid waste of energy, an underwater scooter was used by the authorities' engineer to make a detailed survey, yard by yard, along the whole length of the pipeline, before clearance was given for the release of the buoyancy tanks. The channel blasted through the rock reefs and outcrops was such that the undulating profile of the pipeline would not be flexed to a sharper radius than 1,500 feet. Any remaining hollows were to be packed with small stones or concrete-filled bags to provide a firm and continuous support for the line. The exact position of every one of these hollows was logged on the spot. A marker buoy was attached to a length of rope on each of the buoyancy tanks. The other end of the rope was connected to a cutter, which would shear through the strapping around the tank when the rope was pulled. By pulling on a continuous cable running the length of the pipeline, the marker buoys were released in succession. As each one surfaced, so the rope attached to it was passed to the winch on the barge. With a haul on the rope, the strapping was sheared and the buoyancy tanks released. The tanks were towed ashore in groups and landed by crane. Meanwhile, the diffusers for the end of the pipeline were being assembled. There are 4 3-inch diameter, 3-foot high vertical outlets on each pipe. This was calculated to assist the dispersion of effluent in the sea. The assembly was to be bolted to the flanged ends of the line in 80 foot of water and chained to 2 concrete anchor blocks. The complete assembly, suitably buoyed, was towed out for the final stage of this unique pipe-laying job. At the same time, back on shore, the welders were busy connecting the land pipeline to the 4 sea pipes against the background of the shore valve house, now covered with earth as protection against the possibility of a chance hit from the ranges. Inside the valve house, the twin landline pipes were divided. The 12-inch outer pipes, carrying the non-active effluent, branched through reducers to 2 6-inch pipes ending 50 feet beyond low water. The 2 inner pipes carrying the active effluent continued to the diffusers 2 miles out. From the shore valve house, the 4 separate 6-inch pipes were laid across the shingle and through the trench which had been used for launching. They were covered with concrete and filled in, after which the sheet piling to the trench was to be cut off below normal beach level, restoring the beach to its original appearance. Although from the brake pressure tanks at the highest point in the landline, effluent flows by gravity, the pipelines are kept running full by controls in the shore valve house, in which there are also flow meters, monitoring and sampling equipment. Soon there will be few signs of all the recent activity. Effluent will be safely discharged to sea, and the intervening countryside will look very much the same as it did before the new research establishment came to Winfrith Heath.